Welcome back. We're going to conclude our look at the gastrointestinal tract now by reviewing some of the physiology of the small intestine and the colon, as well as the rectum. Before we go directly into that, I want to pay a visit one more time to the omentum. It's an organ that gets a very short shrift in most courses, and such an important one that I'd like you to take a look at it in closer detail, because its physiology is really one of protecting the entire abdominal contents. If you look at the first slide, this is a picture of what the abdomen would look like if it were opened widely, if we made a long midline incision here, and we had some helpful medical students to pull the abdominal walls apart and open it so you could see the whole abdomen, and you actually can do this in a big operation. Here's the edge of the stomach. Hanging down from the bottom edge of that stomach is the greater omentum. It's shown here mostly as fat, which it is primarily. It has some fibrous tissue, and you can see the vessels. It's vessels that feed the fat. Fat is a metabolic organ and needs a blood supply. Is visible through this person. So this is not an overly obese person, because you would not be able to see the vessels in somebody very, very fat. The omentum is a place where fat gets deposited for storage and protection. People often wonder why, when they've lost a lot of weight and they think their abdomen should be a lot smaller than it is, why it is not. And the reason is they've still got a lot of fat in the omentum. That may be the last to go. You can lose some of the fat under your skin, but the omental fat still stays there. Now, this picture is of the omentum completely removed. The artist has taken some liberty and lifted up the liver in a way which you could not do in a normal operation. But the liver being up here is raised to show you something called the lesser omentum, a structure I really haven't mentioned before. That's an attachment of peritoneum between the liver and the upper edge of the stomach. And all the great vessels that run to the stomach and to the liver are running in this omentum. If we go down to this picture, now the artist has taken the omentum in his fingertips and lifted it up the way actually you might have to do if you wanted to get at the intestines during an operation. We don't actually lift it out of the body, but we do pull it up and tuck it away. And this shows its attachment to the colon. Now, if you remember that in the first side of this omentum, it was attached to the stomach, so it runs down, kind of folds under and sticks to itself all the way back up, and then stops here at the colon. Therefore, there's a space between the stomach and the top of the colon, and we can get to that space surgically if we want to get inside and do work behind the omentum. So as I mentioned, this is the guardian of the abdomen. This is the place that plugs up holes and walls off infections and can even stop the spread of some cancers for a short period of time. It's an emergency organ. Let's move on now and look again at the physiology of the small bowel, the duodenum, jejunum, and ileum, and basically look at the processes again of digestion and absorption. The mechanical phase in the small bowel now should be very clear in your mind as a process of both segmentation as well as peristalsis. Segmentation occurs when we line up two contractions, and they're usually about that far apart, just a few inches, and it completely isolates both the top and the bottom of that bolus of chyme from the one below it and the one above it. Within that segment, we get churning, we get mixing by the plicae circularis, and we get the little digestion that's going on right there, and maybe some absorption. Further on down you go, the more absorption, the less digestion, because it's completed as you move through. The term peristalsis, which is more familiar to most people, is the kinds of contractions that move the whole segmentation along the entire length of the small intestine. So we have both going on simultaneously. We're isolating the food, we're churning it up, breaking it down, absorbing it, and then moving the packet along with coordinated contractions called peristalsis. We can hear those. That's what the doctor's listening to with his stethoscope. We can tell the difference between normal bowel sounds, decreased bowel sounds, as you might hear in an ileus, paralytic ileus, that I mentioned last time, or very high-pitched bowel sounds where you have a partial obstruction. The food is being squeezed past an obstruction that's not completely closed, and food may squirt through along with gas, and you hear very high-pitched noises, kind of like you hear in murmurs in the heart when you listen to the turbulent flow. All these contractions are coordinated along the length of the small bowel by that enteric plexus. Refers to muscle, enteric, gut, plexus, you remember, or plexes, plural, where when nerves came together again, fine nerves joined up in a bigger nerve and then became smaller again. You have the brachial plexus, you have the cervical plexus. This is the enteric plexus, and they coordinate all of this. Now, peristalsis is completely under the control of the autonomic nervous system. You have no voluntary control of this at all, and your only awareness of this is in a disease state, when there's hyperperistalsis, when there's obstruction. The normal passage time is about 4 to 6 hours from the duodenum into the colon. Relatively short period of time when you consider that feces will remain in the colon a much longer period of time. There are diseases that affect peristalsis, the rate of peristalsis. We've already talked about the ones that slow it down. Surgeon handling the intestine, infections like diverticulitis, peritonitis, inflammation of the peritoneum, appendicitis, all kinds of disease, including blood in the abdomen. Blood is extremely irritating, but will cause a peritoneal ileus because of that peritonitis. The other side of that are diseases like cholera, food poisoning, all cause increased peristalsis. They speed up the peristalsis. The body wants to get rid of what that toxic object is. For example, in cholera, there are cholera toxins that the organism, called cholera vibrio, passes into the intestine. This is spread by contaminated water. You're all familiar, I would think, with some of the great epidemics we've had of cholera. It was a very long time, by the way, before anybody knew that this was passed in the water. And there was a doctor in London during one of the great cholera epidemics many centuries ago who had a theory that this might be passed in the water. And to prove it, he set up a map of where the epidemics were breaking out and spreading and went to one town pump and removed the handle so that nobody could get their water from that pump, and they had to go to a surrounding town where there was no cholera, and the cholera epidemic stopped. And in medicine, taking a shortcut is called taking the handle off the pump, because that's how this physician proved his point. Other poisons, such as staphylococcal toxin, the famous 4th of July poisonings, when somebody brings a nice big bowl of a mayonnaise containing food, which sits out in the sun all afternoon while people are having a good time, and the bacteria grow rapidly. They create a toxin that you cannot taste. The food tastes perfectly good, and then you have an outbreak with dozens or hundreds of people with severe diarrhea and food poisoning some hours later. All of these are the body's response to rid itself of poison. Not only does it want to get the toxin out of the body and through quickly, it wants to dilute it. So not only does it not absorb the water, it actually pours fluid onto the scene. Again, we hear that phrase, the solution to pollution is dilution. The body dilutes these toxic substances and will make them less irritating. And in fact, there are cases when you don't want to give a patient medication to stop the diarrhea right away because we like to let them get rid of it first. Some diseases are actually improved symptomatically by taking a strong anti-diarrhea drug, but made worse by prolonging the illness because you keep the toxin in the body longer. Now, the body can also run into trouble. People don't die of cholera because of overwhelming infection. They die of cholera because of fluid loss. They can lose so much fluid from diarrhea that without massive IVs, it's impossible to keep up, and they can dehydrate and die in 24, 36 hours. In developing countries, in third world countries, where healthcare may not be as advanced or available, and sanitation is poor, and these epidemics of either infantile diarrhea, severe E. coli epidemics, or cholera, which is still present around the world today, get into a community, what happens is the system is overwhelmed, not the patient system, the medical system, and there just aren't enough intravenous bottles to give all the patients who need it, and these patients die in large numbers. Unfortunately, because it's very easy, if you had the material, to just hold them off long enough until they get better. So that's peristalsis in its best and worst aspects. We now come to the chemical digestion of the small bowel. And go back there and remember that the chyme in the small bowel is primarily a conglomerate of partially digested hydrocarbons, which are carbohydrate foods, lipids, fats, and proteins, which are chains of amino acids. That's the basic components of our food and our diet. The digestion has to be completed within the small bowel because the colon is not set up to absorb all this material or any nutrients in any significant extent. If you remove, for example, too much small intestine, you have a problem called the short bowel syndrome. It has nothing to do with the colon. There's a disease that is similar but different from ulcerative colitis called Crohn's disease. And it's an inflammatory disease that can be in the colon, but it can also be in the small intestine. It tends to be segmental. It comes in patches and it recurs. Now, one of the problems we get into is we can resect a disease segment if the patient has a complication, isn't responding to medication. Sew the ends together, the patient's fine. Instead of 32 feet, we now have 28 feet. But a year later, we may be back resecting another 3 or 4 feet. And we can get to the point where the patient does not have enough length to complete absorption. Keeping the whole colon doesn't matter. The patient can still not absorb nutrients in the colon, no matter how long it stays there. This is the converse. I said you could remove the colon and the patient can learn to absorb water in the small bowel, but the reverse is not true. We have to be very careful about how much small intestine we remove in disease states, or in a case where somebody may throw a blood clot to their major artery, superior mesenteric artery, and knock off the blood supply to that small intestine. You cannot blithely resect. You have to go in and maybe try to reestablish blood flow by removing the clot, because you may not have enough small bowel for a normal life. Now, the specific chemical digestion plays a part here. The polypeptides are the short chain amino acids. We took the proteins higher up, denatured them with acids, so we opened them up from their geometry, which was all coiled and twisted, and exposed all the links between the amino acids and then shorter chains, which are called polypeptides. So they arrive because we've broken a lot of this down in the stomach with pepsin and hydrochloric acid. We continue the breakdown in the small bowel, and this is activated by the pancreatic enzymes, trypsin, chymotrypsin, which you've heard of already, and elastase, which breaks down the elastin fibers. All three of these are necessary because they each play a different role. Why do we have 3 different types of enzymes just to break down proteins? There are different amino acid sequences, and all these amino acids are different shapes and have different kinds of connections, and each of these enzymes work in different places. So in order to get complete digestion and break them up into either single amino acids or short chain polypeptides, we need different enzymes to complete it. Now, we looked at the brush border on the cells of the small bowel before, those very tiny millions and millions of little hairs. They also excrete some more peptidases. Peptidases will break down the peptides. They're aminopeptides and dipeptides, which are 2, and they complete the splitting of the amino acids. So that completion is done right here in the small bowel. Okay, by this time now, we have molecules that are small enough to go across the cell into the bloodstream and then into the cell of the body that we're feeding. I'll show you a picture of that in a little more detail on how that's done. Those are the proteins and the polypeptides, the amino acids. The lipids, or the fats, are composed mainly at this point of triglycerides. We've talked about them. Those are 3 fatty acids on a glycerin background, and backbone, I should say. And we split those off with pancreatic lipase in the small bowel, usually leaving one of those attached as a monoglyceride, which is a much smaller molecule, and then breaking off 2 chains of what are called fatty acids. And they are also small enough to be absorbed. So we have 1 monoglyceride, 2 short-chain fatty acids. Some of the lingual and gastric lipases have been at work, but they get inactivated very fast. So most of the digestion of the lipids is carried out in the small intestine. They're not water soluble, even at this stage. If you take a bottle of water and a vial of mineral oil, which is a lipid, pour them together, they separate, the oil floats on top. If you take that closed bottle and shake it really, really, really hard, you'll, by physical action, fracture the fat particles into smaller and smaller globules. And what you'll see is a cloudy liquid that looks like lots and lots of little bubbles. Those are the little fat particles. Put that on the table, eventually they'll begin to coalesce. One particle will merge with another to become bigger, 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 and finally you'll have your fat sitting on top again. In this system, we have excreted bile salts from the liver and gallbladder, remember? They come down through the bile duct into the duodenum, and this is an emulsifying agent. An emulsifier is something that breaks down the fat into small droplets and particles, and when that gets into the small intestine, it mixes with the fats, makes tiny, tiny little globules that can then be absorbed across those lacteals and into the body. Now, what happens in some cases when you have a gallstone that comes tumbling down the bile duct and plugs the duodenum? Or you have a pancreatic cancer which shuts off the bile duct, something that prevents bile from getting into the intestine. The patient suddenly starts having, number 1, light-colored stools, because they no longer have the bile pigments that are breaking down. So they have what we call clay-colored stools, and they have fatty stools. The patient will come and say, my stools are floating on top of the water. They're so fatty that they actually float on top, and they tend to have a foul odor because they're not well digested. Digestion has been stopped by the absence of the bile. And in patients who have what are called fistulas, this used to be an old problem, there are certain patients whose bile may be leaking to the outside because of injury. For a while, those patients have to actually drink bile, which is terrible stuff to drink, so that they can get it in their GI tract, or it has to be put in through a tube. Very important to digestion. You have what's called a malabsorption syndrome. Not only will you lose your fat, but you'll lose the vitamins that are dissolved in fat and are required in the GI tract to be absorbed by the fat so that it can be absorbed by the system. Next, carbohydrates. Those are the 2 now. We've done proteins, we've done lipids. Carbohydrates, which are sugars and starches primarily, are cleaved by these enzyme systems into sugars that are smaller by the pancreatic amylase. This was the enzyme that we saw in saliva first, but the pancreatic was the real big one. And it was the one we measured when the pancreas gets inflamed. Pancreatic lipase cleaves those double sugars we looked at. We looked at the complex double sugars and broke them down into the mono sugars that are more easily digested. There's also another enzyme called alpha dextrinase, which is secreted by that brush border cell that we looked at in the last lecture. And that acts on the remaining carbohydrates that may be complex carbohydrates, and it nips off one sugar at a time from one end to the other. So you remember maltose was split into glucose and glucose by maltase. Sucrose was split into glucose and fructose by sucrase. Lactose was split into glucose and galactose by lactase. Now, there are patients you've probably heard about, because this has become a much more popular diagnosis lately, who don't have any lactase, or they have very little lactase. They cannot break down the lactose. And so those patients have what is known today as lactose intolerance. And the lactose is a very good medium for the bacteria in the body, in the bowel, to ferment the lactose. And these patients have lots of excess gas. Very uncomfortable, very disturbing. They get diarrhea, bloating, and they have to avoid products that contain lactose because they can't handle it. Let's look now at absorption. We've talked about now mechanical digestion. We've talked about the chemical digestion in the small bowel. And now we have this third process called absorption, which is going on. This is a really interesting slide. It's obviously a gross simplification, but it's how the nutrients are moved across the epithelial cells of the villi that absorb them. So this cell is lining the interior surface of the small bowel. Has a microvilli or brush border, indicated far fewer, of course, than would be normally seen. This is the side which is deep to the surface, and the blood vessels and capillaries are on this side of the cell. We have to get food across into the blood. This is the lumen. There are different mechanisms for all of these. If we look at glucose and galactose, when it breaks down, there's something called a secondary active transport with sodium. So there is a mechanism that requires energy, that requires calorie, because it is a chemical process that has to be driven with some energetic force. And it uses sodium to take these sugars across. So it's a secondary active transport. The active transport is not exactly operating on this molecule, but sodium attached to that molecule. And then it gets into this side, and it's still inside the cell, will not diffuse passively. It needs some facilitation, which requires more energy. So these are energy dependent. Hopefully you're getting more energy than you're giving. Fructose has facilitated diffusion. It does not need active transport here. It can go right across. It's just a different sugar, different shape. So those are the sugars. If we move down here to the amino acids, which if you look at here's a tripeptide, a dipeptide, and an amino acid. Bigger still would be our polypeptides and then our proteins, but we've hopefully gotten most of them down to these small sizes. A simple amino acid can get in with active transport, in other words, a whole chemical process just devoted to that, or a secondary active one just like glucose with sodium and get into the cell, and it now can get out on its own, no further energy required. The dipeptides will require a secondary active transport, and they go in with a hydrogen ion. Remember, that's the ion that comes off it's basically a proton that comes off in the acid part of the reaction. Short chain fatty acids go in by simple diffusion. We're down in the lipids now. This micelle is referring to the little globule that's been dissolved with the biliary salts. That's called a micelle. And you have long chain fatty acids and monoglycerides. Those are the ones we saw, 2 fatty acids plus a monoglyceride. And they go in by simple diffusion. But they are moved across by another process called a chylomicron. They're picked up in the chylomicron. And look, they're not moving into the bloodstream. They're going into a lacteal, which is connected with the capillaries of the lymphatic system, not the blood system. So you have a combination here of both active and passive absorption, having to do with both energy-dependent processes, much more complicated, obviously, than this slide shows, and then some that are simple diffusion, where you're moving across an osmotic membrane to an area of lesser concentration and trying to equalize that diffusion passively. Now, there's a balance sheet that has to be paid for all this. and it has to add up at the end of the day very, very carefully. There's a certain amount of water produced and a certain amount of water excreted and absorbed and a certain amount of water defecated, and this all has to balance very, very carefully, or we become either bloated or dehydrated, one or the other. If you look at this one, this is probably the easiest way to sum it all up. Here we have everything that's ingested and secreted on this side, and we're going to go to excretion later. We have approximately a liter. A liter is almost equivalent to a quart of salivary secretion, the 3 sets of salivary glands in your jaw, the parotid, and then the 2 under your jaw that we have looked at earlier, secrete a liter. That's an enormous amount just to lubricate and begin the process of digestion. We drink, most people will drink about 2.3 liters a day. This is the average. Now that's not just in liquids. Actually, most people don't get enough liquids by mouth, but it's more than made up for by the water that's in the food you take. So when you eat an apple or an orange, that counts on your liquid balance sheet as well. And that's in the neighborhood of this 2 to 2.3 liters. Gastric juice is an enormous amount. We put out 2 quarts or 2 liters of gastric juice per day. Another one, bile, 1 whole liter of bile going down here or resting in the gallbladder, which only holds about 2 ounces. Pancreatic juice, another big one, 2 liters. And intestinal juice secreted from those brush border cells and the crypts of another liter. A total of between 9 and 10 liters a day in the average person. This is usually calculated for what we call the ideal man, and that's a 154-pound, 5'10" person. So when we make these numbers up, that's what we're talking about. Of course, you vary them later. On the other side, which is the absorption side, we will get back 8.3 liters in the intestine. So as this stuff goes through the intestine, you'll notice the intestinal juice was only putting out a liter, but it's picking up 8.3. So the absorption of these molecules includes some water with it. It's an obligatory water. And then the remaining water that's squeezed out of the feces is only near another liter. This is about 9.2 when they compare it here. And then you have some excreted in the feces, which is very little because the feces is mostly dry, just enough to be lubricated. So look at this balance. You see the importance of the small intestine here in getting both absorption and excretion balanced out. It takes very, very little in the way of abnormalities to get this fluid balance messed up. And the most common serious kind is when we don't absorb enough of it. Clearly, it would be diarrhea. This is the one that upsets the balance in a very serious way. Many, many diseases cause it. Lots of viral illnesses, bacterial illnesses, toxins cause diarrhea that really can be upset the balance and be lethal if not taken care of. The other side of this is rather rare. It occurs in cases where people just ingest too much liquid at a time. One of the most distressing is a habit that college students have gotten into at their parties in seeing how much liquid of a non-alcoholic type they can chug at one time. The alcohol is bad enough because that poisons and depresses the system to a dangerous level. But some students have taken up to a gallon of water and drank it through a funnel as fast as they can for amusement. What happens then is you have water with no sodium content. It's absorbed rapidly. To get rid of it, stomach will pick it up, small bowel will pick it up, and you get such an inrush of plain water that the sodium levels and other electrolytes in the blood drop precipitously, and there have actually been deaths from this before these patients can be treated. So other forms of overingestion of liquid are quite rare. It's really a self-inflicted wound most of the time. We can do it non-gastrointestinally. We can mess up the infusion of intravenous fluids to patients, but that's not a function of the GI tract, and that's not where we are now in this. The regulation of both the secretion and motility is a function of the autonomic nervous system, and it's a reaction to the presence of the chyme, the amount of chyme, which distends the GI tract. We remember only distension causes pain, so that's the only signal we have. It's a good signal because that's the one that's going to get us in trouble. It's also mediated by that myenteric plexus of nerves that will not only coordinates motility, but signals distension. Parasympathetic impulses, again, mostly upregulate the GI system because that's the system that's rest and recovery. It's the one part of the parasympathetic system that is excitatory, as opposed to, let's say, in the heart, where it's relaxation. Sympathetic impulses decrease the motility and the secretion for the fight-flight reaction. Finally, there's something called vasoactive peptide, or VIP, which stimulates secretion. It's just another enzyme that comes out in the digestion process, which gets into the balance. It's just a huge mix of neurological and humoral and intestinal enzymes, which are chemicals that are involved in the chemical process. Although they may not be used up in the process, they are involved in moving the equilibrium one way or the other. And hormones, which are signalers to the process and don't get used up as much as they do get inactivated by the chemical events. Now, the colon, rectum, and anus, the function is rather more simple. We have the absorption of water, so that if large amounts get into the colon through the small bowel by mistake, the colon will be able to get that water back into the system. And basically, it's a storage vehicle that makes the predator's life more convenient for the elimination of waste. The mechanical digestion at that point is interesting too. There's a couple of signals that are very primitive. When the stomach is distended with the first bolus of chyme, you remember all the signals that went around to the small bowel, into the pancreas, into the hepatobiliary tree. Lots of signals went around to tell the small bowel what to do, and they were signaling back and forth with both positive and negative feedback loops. However, when the stomach is distended, another gastroileal reflex signals the ileocecal valve to open and let the small bowel contents in. It wants to get rid of what's ever in the small bowel because it's saying, I'm getting a meal, you're getting a meal, and we need to make room. We need to move this process on. At the same time, there's this haustral churning that we saw in the colon that starts really moving things along. What happens now when you get up in the morning and you either smell the coffee or you take that first cup of coffee, the first bite of your breakfast, you often get a churning and the first urge to move your bowels. There's something called the gastrocolic reflex. And again, it's the predator needs time between eating and defecation because he's got other things to do. And he also has to signal that there needs to be room. So during the first segments of the gastric phases of digestion, the stomach has to signal all the way down to the colon and say, get empty, get ready. And this is why when we eat food, we often have to defecate very shortly afterward. That is not the same food. The food that's in your stomach takes more than a day in many cases to get to the rectum, but it is the colon that's making way for that food to come in. When a segment is distended in the colon, it reacts by contracting. And the gastrin released in the stomach also opens up the ileocecal valve. The gastric reflex then moves the chyme along. Anything semi-solid we call feces, and it's usually there about 5 or 10 hours, just getting more solid in the colon. And we get something, if we want to move it quickly through, it's called mass peristalsis. The final digestion in the colon is mediated by bacteria, not chemical digestion. There's basically nothing going on in the colon. So when we go from this portion of the colon, which we have just finished our chemical digestion, all the way over to this side. By the time we get here, we have fermentation and bacterial digestion breaking down the last particles, getting this into a state that is ready for digestion, product of which is some methane gas, some hydrogen gas, and other actual flammable gases that we pass as flatus. And the fact that they're flammable actually is something we consider in surgery where we use electrical current. Sometimes you can have an explosion from these flammable gases if you're not careful with the use of electric sparks and current during surgery. We've already talked about the fact that most of this gas is swallowed gas, so that we use the passage of flatus as a signal that the whole GI tract is working. Now, one of the other interesting things is that this whole fecal formation and storage has a lot of effects on the physiology. Things that we take in through our GI tract and are stored and concentrated in the feces are going to be in contact with our intestinal mucosa, especially the colon, for a long period of time. Therefore, if we're taking in carcinogens, substances that cause cancer or have other bad effects, it's going to be sitting there against the colon. And this may be why we get cancer in the colon. And if we look at our slide again, if you look at where colon cancers occur, the vast majority are between here and the rectum. This is where they sit the longest and are most concentrated and spend the most time in the highest milligrams percent against the colon wall. And it just progressively decreases as you go backwards to the cecum. There are cecal carcinomas, but they are far less. 65 or more % of all colon cancers are within reach of the finger or the short sigmoidoscope. So this tells us something about the physiology going on this side of the colon. Now, there was an epidemiologist named Dennis Burkitt, who was a British physician who went to Africa and was doing epidemiologic studies, and he noticed something rather interesting. There was almost no colon cancer. There was virtually no diverticulitis, and he didn't even see appendicitis. Later, he made more observations about the low level of coronary artery disease, and he started studying what was going to be different there than he saw in Europe and in the United States. The answer turned out to be the passage of the feces through the colon. In the populations in emerging societies, again, third world societies, they do not have the luxury of processing their food. Back in Burkitt's time, which was in the middle of the last century, we tended to try to show or demonstrate wealth by processing food. People ate much more white bread. They never ate whole grains. They processed rice. They made sure that they got rid of all the hard, undigestible material from food, whereas people in Africa did not. They ate everything just as it came from the ground. So they had very rapid passage because they had what we now know are the undigestible products of these plants, the outer coats, the husk, the cellulose that we can't digest, and they had large, bulky bowel movements several times a day. Tended to be non-foul smelling because it didn't have that long fermentation process. It tended to be not diarrhea if there wasn't a disease state, but just well-formed, bulky stools. He then looked at the typical Western European or American who tended to be relatively constipated. He said there's got to be a connection here. And over the years, of course, in the last half of the last century and now, we know that this bulk, these non-digestible particles of food are almost like what has been called a colonic broom. It's a cleaning process. There has been a lot of question whether this is purely the reason or there are other reasons, but certainly we know that there is a markedly lower incidence of colon cancers, diverticulitis, appendicitis, and coronary artery disease, because these types of soluble and insoluble, in other words, dissolvable and non-dissolvable fiber, tends to carry with it lots of fats and things like cholesterol. So those patients also lowered their cholesterol. And we know today that if you put a patient on a lot of soluble fiber, certain patients will have their cholesterol come down. Those patients that are not making it in their liver into excess, but are actually absorbing too much from their diet. This was a very important step in epidemiology and in the prevention, which is where we would like to be. We don't want to be at the cure side of disease. We really would much prefer to be at the prevention side. So that's one side of the story of your colons. The other side is that we don't see very much is that the rectum is an excellent absorber of water, even better than the colon. It has an extremely rich blood supply. Any surgeon who operates down there will tell you bleeding can be a big problem because of the enormous blood supply. We've taken and made use of this fact. If you take an empty rectum that doesn't have feces in it and put something in there, it will be rapidly absorbed into the bloodstream, sometimes almost as fast as if you've given it intravenously. This is why, for example, if you have babies who can't absorb or can't swallow an aspirin, you can take that aspirin in a suppository, put it in the baby's rectum, and it'll be gone a few minutes later, and it will be absorbed into the bloodstream. We give lots of medication that way. We can give morphine that way, opium drugs, narcotics. We can give almost any drug that's not too irritating in the proper vehicle rectally. And again, in the third world countries where we want to rehydrate patients, and we don't have the luxury of intravenous fluids and intravenous medications, you can rehydrate them by mixing salt in water, making a saline solution, and giving the patient an enema and asking them to hold it and not expel the enema. And all of a sudden, after a few minutes, the feeling that they have to move their bowels is gone. Because when they're dehydrated, there's a lot of movement across the blood supply to the rectum that will allow them to absorb the water. Another very useful device using the physiology. The last part of the physiology is the physiology of defecation, which is worth review. You've seen the anatomy of the muscles. The feces basically ends up in the rectum via this mass peristalsis, and at the last comes from the sigmoid, the last turn, and is dumped into the rectum when it's ready to be excreted. There are receptors that signal distension to the brain. It's a conscious perception. We're not really aware of masses in the rest of the colon, but when we get that tenesmus, as I've defined for you in the last lecture, that's the feeling that I have to defecate. We usually restrict the word tenesmus now to the patient who feels that they have to defecate but can't. That might be the patient who's either extremely constipated or has a tumor that they're not going to be able to get rid of that way. They mimic the feeling. The defecation reflex is initiated by parasympathetic stimulation from the spinal cord that contracts those longitudinal rectal muscles and pulls them up, trying to relax the segment ahead. Then pressure increases in the rectum, and then it's added to by your voluntary contraction of the abdominal muscles. That's the voluntary part of the defecation reflex. So the parasympathetic stimulation relaxes the internal sphincter of the anus, which is involuntarily, and then your conscious pushing or pressure is what also relaxes the external sphincter. You don't think about it consciously, but you're actually consciously doing it. It's important because it's voluntary, and therefore you can control the time. When the internal set of impulses from the parasympathetics and the internal sphincter says, I want to move the bowels, you can most often overcome that by tightening the external sphincter and postponing that time to when it's more convenient. Now, this can be overwhelmed with mass peristalsis, diarrhea, or weakened muscles. People's muscles can be weakened by age and by disease or by trauma, and those patients are what we now call incontinent. They're unable to keep their feces in when they want to. Very, very disabling and unpleasant situation, which sometimes can and sometimes cannot be rectified. But again, this is an evolutionary result of the fact that the predator needs to have more time between eating and defecation to do the things that predators do, which brings us right up there with some of the great animals. We are the #1 predator. That brings us to literally and figuratively the end of the GI tract discussion. Next time we'll move on to another system entirely.